Alright, so at this point we skipped chapter 5, you should have finished chapter 4, and now we are going to jump into chapter 6. So chapter 6 starts talking about trigonometric functions, and it begins with a discussion of right triangles and acute angles. And just some notation, when we talk about defining or labeling unknown acute angles, we, instead of using the American alphabet, we usually use the Greek alphabet. So alpha, or beta, or gamma, or theta, or phi, or any other Greek symbol is just used to represent an unknown angle, kind of like x is an unknown value in an algebraic equation. Alright, so when we start talking about right triangles, what we're talking about are triangles that have one right angle. And in terms of trigonometry, the side that is opposite the right angle is what we call the hypotenuse. Okay? It's always the hypotenuse. Now, depending on where your unknown angle is, for example, if we call this angle theta, the side that is attached to angle theta is what we call the adjacent side. And the side that is opposite the theta is what we call the opposite side. Now, opposite and adjacent can flip based on where the unknown angle is. Certainly you can see that if this were the angle that we were looking for, this would become the adjacent to beta, and this would become the opposite of beta. So it matters where the unknown angle is. Now, we have some really basic trigonometric functions that are listed nicely on page 479. And the idea here is that the sine of any unknown angle is the opposite over the hypotenuse. The cosine of any unknown angle is the adjacent over the hypotenuse, and the tangent of any unknown angle is the sine over the cosine. Then we have inverse functions. So the cosecant, not cosine, cosecant, is going to be the hypotenuse over the opposite. Let me just make sure I have that correct. That's correct. Then we have the secant, which is the hypotenuse over the adjacent side, and then we have the cotangent, which is cosine over sine. Or, in terms of opposite, tangent would be opposite over adjacent, and this would be adjacent over opposite. Excuse me. Okay, now, trig functions are useful because what they help us do is identify unknown lengths of sides of triangles. They also help us identify unknown angle measures. So for example, if we have this triangle, and notice that we're only working with right triangles at this point. That's an important distinction. We're going to call this side alpha, and we'll call this side theta, or angle theta, excuse me. The length of this side is 12, this is 5, and this is 13. The directions are, I think in the text it asks you to find the trig values of theta and alpha. We're just going to look at one. So let's find the values, trig values of alpha. So the idea here is if we wanted to know the sine of alpha, it's the length of the opposite side is 5, divided by the length of the hypotenuse, which is 13. So what you would do is you take your calculator and you do 5 divided by 13, and I don't have my calculator, let me grab my calculator. And you get 0.34 or 3846 approximately. And then the idea is you're trying to solve for alpha, so you would essentially divide both sides by sine, and then if you recall your inverse exponential rules, what you end up with is alpha is equal to what we call the inverse sign of 0.3846. And if you look at your calculator, your inverse sign is typically the second key or the key above the sign. So you would take the inverse sign of that and you would end up with alpha being 22.62. Finding the cosine of alpha, we want the adjacent side divided by the opposite. So that would be 12 divided by 13. And again, what you want is, in fact, the inverse. When you do the algebra, alpha is equal to the inverse cosine of whatever 12 divided by 13 is. And so on and so forth. Tangent, you would put in cosecant, secant, and cotangent. It's just plug and chug. Just make sure that you use the inverse function on your calculator. Just as a note, the trig values of theta only depend on the measure of the angle of a triangle, not on the size of the triangle. Don't forget that when you sum all of the angles of a triangle, it doesn't matter how big or small the triangle is, the sum is always 180. So what I just stated sort of follows along that vein, where we don't care about the size of the triangle, it only measures on the angle itself. All right. We can find the other 5 trig function values of an acute angle when one of the function value ratios is known. So the idea is, if you can figure out the sine of an angle, or the cosine, or the tangent, or the cosecant, or the secant, or the cotangent, any one of them, you can figure out what the other 5 trig functions are. So let's look at an example. If we know that the sine of beta is equal to 6/7, and we know that beta is an acute angle, we want to find the other functions of beta. All right, so here's the deal. We know one of the trig functions. And if you recall, sine was opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent, cosecant, hypotenuse over opposite, secant is hypotenuse over adjacent, and cotangent is adjacent over opposite. If the sine of beta is 6/7, we know that 6 is the opposite side, and we know that 7 is the hypotenuse. So using these, we can actually find the rest of our trig functions. You just plug everything in. So cosecant would then be 7/6. Now, we also probably want to know the length of the third side so that we can figure out what the adjacent is going to be. So I think in the text it gives you a picture on page 481, and we have beta down here in the corner here. We have the opposite side being 6 and the hypotenuse 7, and this is unknown. Now, you have to use a little bit of prior knowledge to figure out this last side, and since it's a right triangle, we're going to use the Pythagorean theorem. So we can say that a squared plus 6 squared equals 7 squared, a squared plus 36 equals 49, subtract 36 from both sides, a squared equals 13, so a is the square root of 13. So coming back over here, we know our hypotenuse is 7, and we know that a is the square root of 13. We know that a is the square root of 13. We know that our opposite side is 6. We already have this one, this was given. Adjacent, square root 13 over the hypotenuse, which is 7. Opposite, which is 6, over adjacent, which is square root 13. So once you know two sides, what you can do is figure out pretty quickly what the third is for a right triangle and an acute angle using the Pythagorean theorem, and then you just plug everything in. It's pretty straightforward. There are some standard angles that we're going to use a lot in trigonometry, the 30-degree angle, 45 and 60-degree angle, and it's probably well worth your time to look at page 483. There's a table at the top of the page that talks about just some real simple sine, cosine, tangent for 30, 45, and 60-degree angles. So again, page 483. You want to look at the trig functions, the basic trig functions for 30 degrees, 45 degrees, and 60-degree triangles. That is important.